So, hi everyone. Welcome to the next episode of Dark Chatter. Today we've got Maura Ramirez Quezada from, who recently completed her PhD at Durham University at the IPPP. Thank you very much, Maura, for being with me.
Thank you. Thank you.
Just quickly sort of introduce yourself, introduce your kind of general research interests, and then we'll start talking about a recent paper that you had out.
Well, I'm Maura. I'm from Mexico, and I did my PhD in Durham University. I just finished in February, and well, basically my work has been in neutrinos and dark matter. So we've been studying some processes, some neutrino decays to see if we can see something measuring the circular polarization of these gamma rays that are produced in neutrino decays. And recently I finished a paper with a group in Melbourne about dark matter capture in compact objects. In this case, it was white dwarfs. Yeah.
So can you tell us a little bit about how you sort of ended up working with this group in Melbourne, and what drew you to this subject area of dark matter and white dwarfs?
Yeah, well, I started working with Sandra Robles. She's from Peru, and when I was in my first year doing my PhD, she went to Durham for like a research visit. She was visiting some people there, and she was in my office, so we just became friends. We actually didn't talk about doing something together, but after 1 year, I actually was in Sydney visiting Celine Boom, and she was already in Melbourne as a postdoc. She's like 2 years or 3 years older than me. And then we met there because I told her I was in Australia, and she went to Sydney to visit me. And then it was when we started talking about doing something together. And yeah, it was mostly because I saw so much of her papers regarding neutron stars. So I was like, why neutron stars are just like very important, or why you are looking at neutron stars to set constraints on dark matter. So she explained a little bit, and after 2 months, when I went back to Durham, she sent me an email saying, if you want to work in something, I have some ideas. Instead of neutron stars, they're gonna be white dwarfs. So that's how we started working together. And this project took 2 years. So the first year I was working only with her, learning about the capture rate process and all the background of this. And in the second year, it was when she introduced me with this group in Melbourne that they've been doing neutron stars. And yeah, that's how I ended up working with all of them. Yeah.
Yeah, so I guess the question I have is kind of similar to the one that you initially had. So why are you interested in objects like white dwarfs and neutron stars in the context of dark matter? What's the general reason why?
The general reason. Yeah, well, when I asked this question, the easiest answer she gave me was because these stars are really compact, are really dense, and some of them are in region of the universe with dark matter is even like the density of dark matter is even larger. So these dark matter around the stars can get trapped, can get captured in the star, and they might cause some effects on the star. And that's how by observing this, the luminosity of these stars or some other like temperature, you can set constraints. So that was the basic idea she explained, and of course that's the basic idea behind this work. Just the most important thing is that they are very, very dense, so they can just trap dark matter. Yeah.
So can you walk me through the sort of we can get to because this paper that you've had out recently is sort of fairly it's a fairly detailed paper actually in terms of this sort of wider research area of this dark matter capture. Can you just walk me through the kind of the basic steps of the kind of calculation? So what are the kind of essential processes that lead you to something that you can actually use to set a constraint on the dark matter cross section?
Well, yeah. Well, for me was first of all reading about capture rate, reading about how to compute this in object like the Earth of the Sun or the Sun. But once, if we wanted to have it like an improved work on this, we have to learn about the star. We have to learn about the inner structure of the star, which implies learning about equation of state. So we basically went through a lot of reference talking about how to model these stars. The other important thing was we didn't want to use theoretical star, I don't know how to call it, like we want to use real data. And the next step was looking for some data that shows real measurements of luminosities and temperatures of white dwarfs in region of the universe. So we ended up with the M4 because that's what we found in like many papers and a lot of many measures of luminosities in this globular cluster. And then we kind of compare with some other works regarding that where they also were using these stars, but in a more simplistic way, because they didn't really took into account the inner structure of the stars. And also another thing that we have to learn or we have to like review during the work of this paper was also which kind of interactions we wanted to look at, more realistic things, more realistic operators. And that's why we ended up also working with the EFT operators. And because in this process or in the capture of dark matter in these stars, the dark matter interacts with the nucleus of the element that the star is made of. We also had to look at the form factors and the interactions of this dark matter with the ions in the interstellar medium. Yeah.
So is it fair to say that that you're sort of trying to kind of upgrade the treatment of this kind of dark matter capture in white dwarfs on multiple different levels? So you're dealing with this more detailed model of
more realistic,
sort of more involves maybe like a more complete set of interactions that the dark matter can have, and then also looking at the kind of a real population of stars, which I suppose is kind of captured in the title of your paper, which is the improved treatment of dark matter capture in white dwarfs. So that's I think that covers sort of essentially the motivation behind this. What would you say is the kind of key result that you would want to sort of flag at the beginning when you're sort of introducing this paper to someone? You had a very short period of time to explain it. What's the kind of thing that maybe surprised you the most, or you think is the most interesting result that came out of this?
The most interesting, I think, well, I don't know. That's a very difficult question. But I think the electron result, the constraints on electron, dark matter and electron interaction, that would be like the novel thing in the whole paper. But also the fact that we realized the temperature also changed a lot. It made a change if you introduce the temperature in the capture rate, because in previous works they work at 0 temperature limit. But if you actually see at the temperature of the star, if you introduce that in your calculation, which now they cannot be done analytically, but you have to do it like numerically, you found like a really important change you cannot ignore in some cases. So that I think that was one of the most interesting for me. And also, well, for electrons, it's everything, I will say. And also the evaporation, the mass evaporation, because some papers talk about how you, instead of capturing dark matter, the dark matter flies away, but they don't really estimate properly the evaporation mass. In this work, it's also an approximation, but it's a little bit more detailed than before.
So yeah, this evaporation mass seems to be quite important in this area. Can you describe what the impact of the evaporation mass is on the sort of the final results of the sort of the dark matter models that you can constrain?
Yeah, so as I said before, for example, if you work with the sun or you work with the air, the evaporation mass is really high, is really large. You will get in the sun, I think, if I remember well, it's like 3 GeVs or something. I'm not sure. But in the case of the white dwarf, you have really, really small evaporations. That means that you can set constraints in an accurate way to the sub-GeV region of the dark matter mass, which is not really you don't have that from, at least you don't see that in the dye detection experiments, for example. So that would be the important thing about this evaporation mass, because then you see how low in the mass region you can go, and you see that it improves a lot the constraints from dye detection experiments, and also from if you use some other stars.
Yeah, so I guess we can get into a bit more of the details of the paper. So when it comes to the sort of the general story of these constraints, I guess the idea is that the dark matter gets sort of somehow captured, interacts with the star, gets somehow captured within the star, and then you have this sort of setup of I guess is it fair to say it's a kind of equilibrium between the sort of the capture of more dark matter of the star and then the kind of destruction of the dark matter via annihilation. So is that I guess that equilibrium is sort of how the constraints end up arising.
Yeah.
What sort of restrictions does that place on the kinds of models? Because you're sort of having to rely on the kind of dark matter kind of being captured and then also being annihilated as well.
Annihilating, yeah. Well, in this case, it's because I don't remember, but I think it's because of the time the dark matter takes to thermalize, and it is really short in comparison to the age of the star, if I remember well. And that's why it's safe to make this like this assumption. There are some other works where they don't do that, I guess. No, I think everyone does that. But yeah, it's just to define, or to be able to define a I don't like to call it like dark matter luminosity. It's more like the luminosity, the fraction of the luminosity that you get because of the effects of the dark matter in the core of the star. Otherwise, that definition or that it would not be possible, because then you have to also calculate the annihilation and all this. It will change dramatically. But yeah, that assumption allows you to define this fraction of the luminosity that it comes from the dark matter in the core.
And so the initial capture of the dark matter is sort of relying on essentially the interaction between the dark matter and the material that's making up the stars, so the ions and the electrons. Is that
well, the initial would be more like gravitationally, how the star attracts the dark matter into the core, and once the dark matter is passing through the core, it interacts with the stellar matter, and if after this interaction it loses enough energy, then it gets trapped. And that's what we estimate with the C capture, like assuming that the dark matter is passing through the star and then interacts with the ions. Yeah, but it has to lose enough energy. Otherwise, it will be the evaporation process. Because in the interaction, it would just fly away. Yeah.
So the capture rate is one of the sort of early results in the paper. I'm just going to quickly flip to it because there has some interesting. There's some interesting stuff to talk about. So the capture rate, what you show is essentially it's the capture rate as a function of the dark matter mass.
Mass.
And most, so you do it so a range of operators, and then for scattering on helium and carbon, it looks like for different white dwarf stellar masses. The general structure seems to be that the capture rate increases up to maybe, so we're looking at the nuclear scattering here. It increases up to a sort of a certain mass around maybe like 1 to 10 GeV. Yeah, and then it sort of starts to go down again. What's the general explanation for that?
Well, in general, the suppression comes because of multi-scattering. You will need to implement multi-scattering because when the dark matter is like the mass of the dark matter is very high, you will need more than one single scattering. In these plots, for example, the plot, I think you're looking at the figure 3 of the paper. Yeah, in these plots, you are considering that the dark matter is, you are considering only one scattering, a single scattering. And when the mass becomes really, really high, you will need more than one scattering to improve that. That is implemented in the electron for the electrons, but still not for the ions, because you will need a different treatment. In the case of the electrons, the theory behind that is given for neutron stars, because in the white dwarf the electron is degenerate as is the neutrons in the neutron star. So that's why we haven't implemented that yet. It needs to be worked out. But yeah, that would be the explanation, that for massive dark matter you need to consider more than one scattering to actually get the dark matter being captured. Yeah.
And does that go somewhere to explaining why there are sort of these certain operators which have a slightly different scaling, like either they have a steeper rise or they have a steeper fall off?
Yeah, that comes from the form of the operators, because, for example, the ones that are more suppressed, where is the table? Tables are, if you look at the table 3, you will see that some of the couplings depend, also have Yukawa couplings. And is it table 3? Yes. So those couplings are different from these operators, and that's why in some cases, even though the operator looks quite similar, you get some more suppressed than the others. Yeah. And also the form factor will make they will be different for the different operators, because we are not using any approximation. We are using the complete treatment for the form factors to include the structure of the nucleus. Yeah, that would, the different couplings and the different form factors for each will explain why some of them are different, and when some of them look more suppressed than the others. Yeah.
Yeah. So I guess we can take that, and we can take the discussion that we had about the dark matter luminosity, and then I guess together they sort of form the story of how you get to the constraints. So if we skip now just to some of the constraints that you plot, some of them are sort of remarkably strong, especially if you compare them to the standard direct detection searches, which we think of as being the kind of one of the most powerful ways of looking for these kind of dark matter scattering. But so what's the sort of general how should we understand how these constraints are able to be so good when compared with the direct detection constraints?
In the case of these ions, right? Well, this is a tricky question because I don't remember. I'm just kidding. No, I think it's because we are comparing with direct detection experiments, and in the air there are many things that you have no control, and also the dark matter density that it's in the locally dark matter density, it's very low. So I will say that all these constraints, that you have threshold constraints, the dark matter density, and that also you don't have access to very with dark matter interactions that are dependent on momentum and velocities. You have no access to those kind of things. So that's why in a white dwarf, all these constraints are not really, I mean, you don't have these kind of constraints. And you expect also to have relativistic or dark matter that it's accelerated at some relativistic speed, because the density of the star will make the dark matter to gain this kind of or will allow us to access to this kind of dark matter, right? Interactions. So that's why comparing with the dye detection experiments, you get much better constraints from these white dwarfs, or in general from compact objects. And it's because all these limitations are not really a problem in these objects. Yeah.
One of the things I would like to ask you about actually is regarding figure 10. So it's another one of these constraints. It's the spin-independent dark matter proton cross-section. So we have some of the familiar direct detection constraints here, and then your new constraint.
Yeah.
And then so you're comparing it against this other work. So this Dasgupta et al. What are the differences between your calculation and this calculation?
And Dasgupta. Well, it's, first of all, we use a different white dwarf. He, for some reason, used a 0.49 solar mass white dwarf, but it's not the one who has that gives the right constraint to the dark matter interactions. So we checked all the white dwarfs in this M4 global cluster and realized that the good one was the heaviest one, which is 1.38 solar masses. Another difference is that Dasgupta took into account that the mass and the radius, the mass of the white dwarf, it was like just a solid structure. He didn't take into account the inner structure. Also, as I said before, we didn't use any approximation, Helm form factor approximation for the interactions between dark matter and ions, and Dasgupta used one of them. So that's why the plot looks kind of different. So, but I think the most important one was including the inner structure of the star, and also realizing that the best one that will give the constraint will be the 1.38 solar masses. Yeah, that's the main difference between our work and Dasgupta. Yeah.
Yeah, well, I wouldn't undersell it. I mean, this paper is all about trying to refine the calculations and so, yeah. I mean,
Yeah.
So I guess this really comes back to the story that you're trying to basically improve this calculation across the board. So kind of in that spirit, what would you say is the because I mean this is the science is never done. So what is the next stage for improving it even further? Would you say?
I don't know if I'm allowed to say that. Okay. Sandra is very secretive about the work. It's like, don't tell anyone. But I mean, from the paper, I think the obvious thing is multiscattering to see, because it's done for electrons, but it's not done for ions. So I will say that the next step will be trying to implement the multiscattering to these interactions of dark matter with the nucleus. But yeah, I don't know if I can.
Yeah, no,
I don't know to risk.
I'm more curious if there is still things to do, which I suppose
yeah. But yeah, there's a lot of things to improve still. It's complex. But I think this is a good start. Yeah.
So, but in terms of you and your general interests, is this the sort of thing that you'd like to consider doing more of in the future? So maybe looking at neutron stars and other bodies. I know there's been talk about exoplanets, and of course people have been talking about planets and the Earth and the Sun and things like this. But is this sort of a general field that you're interested in, or what's your take on it?
Well, to be honest, I think this was my favorite subject to look at during my PhD. So I really like it. and I would like to learn, about neutron stars, because I've read the work about neutron stars, but it's I think the most interesting part to me at the moment is, more than the capture, is learn about the star, like learn how to solve the equation state, learn all the properties, because it's kind of like, it's astrophysics, astroparticle physics, and it's also particle physics. So it's, so far I think capture rate, it's something that I can actually now work out, but it will be different if I work with a neutron star, for example, neutron star. So that's that. Yeah, I would like to learn about neutron stars and also exoplanets, or there's even some work about Jupiter as a way to set these constraints, or some other brown dwarfs, or So that I would like to learn more about it. But yeah, it's mostly because I got really into the physics of these objects. It's really interesting. Once you learn how it works, then it's easier to implement to the capture rate. Yeah.
Yeah, I must say that's the part of the paper that struck me the most immediately, is how complex these objects are. I mean, I guess the neutron stars are. I know, is it fair to say that they're maybe even more complex than the white dwarf?
That the white dwarf. White dwarf is a very simple object. The neutron star, as I say, I'm not an expert on that, but from what I've heard from this group in Melbourne, they are quite more complicated in terms that you don't really know, for sure how it works, how is the inner structure. So you have only models, and you can try all these models to set the constraints. Actually, in the group I'm gonna be working on Japan. They are interested in neutron stars, so I guess I'm just gonna learn about it once I got there. Yeah.
Yeah, it's really exciting. I mean, it seems like there's a lot more people getting interested in looking for dark matter in stellar.
There's actually a lot of work. I've seen many papers about capture rate in many objects in the universe, in the sky. There's recently one of done for, I think, from the Earth, the Sun. It's from Garani. It's kind of it's called for celestial bodies, to generalize that is stars, but there are also planets and other kind of objects that can be used to set the constraints. Yeah.
What's the kind of the dream of this sort of part of the field? Is it to eventually find, maybe some population of objects where you do sort of have maybe a level of heating in the objects that maybe hints towards the existence of dark matter, or is that the kind of where the direction within this field is trying to go in, to try and actually sort of discover dark matter somehow in this way?
Yeah, by looking at the changes that might create in the structure, but not in the structure, but in the temperature of the star. And it's not also the temperature. I don't know about other ways, but I've read during my a time when I was reading about this, I also found some people that they estimate the limits in a different way by assuming that the white dwarf or the neutron star get too much mass from the dark matter, that they implode or explode when they become like a supernova. So it's a different way to estimate constraints. But yeah, all of them will require that you learn about the object, and if you want to actually have a more realistic result from your calculations. Yeah, but yeah, it's not just change some temperature. There are some other ways to do it. Some other things to explore.
Yeah, it seems like this field has quite a bright future then.
Yeah, it's on style recently.
Yeah, definitely.
Everyone wants to do it. Yeah. Yeah.
So thank you again thank you very much for talking with me about this very interesting work. I hope that you can come back to Sydney at some point. We'd be very pleased to have you.
Yeah, it would be nice once all this COVID thing is done.
Yeah, exactly.
I want to go and visit Celine.
Yeah.
I will go and visit Celine. Yeah. Yeah.
Yeah. Well. Thanks again, and best of luck in your new position. And
Yeah. Thank you.
And we'll see you all next time.
Yeah. Thank you for inviting me to do this.